Hi, my name is Ben, and I will be presenting my kinetics assessment for AP Chemistry. This presentation will look at the conceptual foundations of reaction rates and the mathematical frameworks used to describe them. To start, we need to look at collision theory. For chemical transformations to occur, particles can not only collide, but must do this with sufficient energy to overcome the activation energy barrier while maintaining a correct molecular orientation. If they do not have the proper orientation, the molecules will not stick to each other and will bounce apart. An effective collision has the necessary amount of energy and correct orientation to bond. We can see this in real-life examples of catalysis. A catalyst aids a reaction by providing an alternative pathway with a lower activation energy, therefore increasing the frequency of effective collisions without being consumed in the process. As seen here, a catalytic converter does this by aiding the oxidation or reduction of emissions from a car without actually consuming the precious metals within. This graph here also shows a reaction with and without a catalyst. Next, we look at mechanisms. A complex reaction is almost never a single event. Instead, it happens through a mechanism, which is a sequence of smaller elementary steps. A mechanism is only considered valid if the total of these individual steps added together aligns exactly with the overall balanced chemical equation, meaning that the stoichiometry is preserved throughout the process. Rate determining step. With any mechanism, the rate determining step, or RDS, acts as the primary constraint on the reaction's velocity. Similar to a bottleneck in a physical system, the overall rate of reaction is limited by the slowest elementary step. Therefore, the experimentally determined rate law must reflect the molecularity of this specific step. This was seen within our rate of reaction lab as the reaction between I2 and S2O3 was almost instantaneous, while the negative iodine ions in S2O8 was much slower, therefore acting as the rate determining step for the reaction. This is also an example of a mechanism as it broke down into smaller elementary steps. Next, we look at differential rate law versus integrated rate law. We identify these rates using two separate equations or models. The differential rate law describes the relationship between the reaction rate and the reactant concentration. In contrast, integrated rate law utilizes calculus to relate concentration to the passage of time. These are often looked at graphically. For a first-order reaction, a plot of the natural log of concentration versus time will yield a linear relationship, allowing us to calculate the rate constant k through the differential rate law. This is a comparison between the two. What are orders? Within these laws are reaction orders. A zero-order reaction means that rate is independent of concentration. A first-order reaction implies a direct proportional relationship, while a second-order reaction is when the rate is proportional to the square of the concentration. These values are essential for understanding sensitivity of reaction to its environment and necessary to determine the value of K. Next up is the example problem. To demonstrate these principles, we can examine the reaction between nitrogen monoxide and chlorine gas. The data here has been adapted from Glaser Tutoring Company and converted to molarity per second. These rates were then multiplied by 100 to get slightly easier numbers to work with. So as you can see here, the reaction formula is up at the top, and we have rate is equal to K times molarity to the X and molarity to the Y. The X and Y values are the orders, so first, second, or 0 would go up there. The first step we do is we have to solve for X on the molarity of NO. We first do this by putting rate 2 over rate 1, and we set this equal to their differential rate law. So we set this equal to K times the molarities to the X and to the Y. We then can cancel out the K's and the molars to the Y, which leaves us with 4.01 times 2 to the X. X would then be about equal to 2, which means NO is second order. We then need to do this again with putting rate 3 over rate 2. So we have the rates here, and then we can cancel out K's and the molarities to the X. This leaves us with 1.99, which is equal to 2 to the Y, which means Y is about equal to 1, which that would then mean Cl2 is first order. To determine which rate to put on top, we had to use the larger rate of the two we were using. We then take this and we plug in and we determine our rate law. So rate law is rate, which is equal to K times the NO to the order and Cl2 to its order. So rate is equal to K times NO to the squared, and Cl2 has no exponent because it's just 1. We can then rearrange this where K is equal to rate initial divided by the molarity of NO squared and times the molarity of Cl2. We can then plug in one row or trial, which I plugged in row 3. So K is equal to 0.0253 molars a second divided by 1 molar squared times molar. That would then give us K is equal to 0.253 molar to negative 2 times second to the negative 1. To determine units, we did the molars a second divided by molar squared times molar, which means molar a second times 1 over molar squared times molar, which is molar cubed. So we would have 1 over molar squared times second, which is also equal to molar to the negative 2 and second to the negative 1. This reaction would have two possible mechanisms. The first is comprised of these two steps, the first of which between NO and Cl2 being fast, where one NO bonds and they just add up to each other. And then the second step would be slower, where NoCl2 and NO come together and form two NoCl molecules. There could also be a single step mechanism, but it would just look like the reaction equation. These are the sources. By comparing experiments 1 and 2, we observe that the concentration of NO is doubled while Cl2 remains constant. The rate increases by a factor of 4. This is also indicating that the reaction is second order through observations with respect to NO. Comparing experiments 2 and 3, doubling the Cl2 concentration results in a doubling of the rate, confirming a first order relationship. This confirms our rate law of rate is equal to K NO squared times Cl2. Thank you for watching this video, and I hope you learn more about kinetics.